We talked about gravity earlier, and we talked about how gravity and weight, according to your textbook, are the same thing. Easily calculated by multiplying the mass by the acceleration due to gravity, g. That works on the surface of the Earth, but that's not really the way you want to calculate gravity ideally. Newton came up with a way of actually calculating the gravitational pull between two objects, and he called it his law of universal gravitation. Now, Newton's big breakthrough was assuming that all of the mass of an object is located or concentrated at the object's center of mass. So the entire Earth, if you're outside of the sphere of Earth or on the sphere of Earth like we are, all of Earth, all of the mass of Earth pulls on you as if all of the mass was at the center of the planet. So the distance, r here, between the centers of mass of two objects is used when calculating the force of gravity. So I'm not interested in how far I am away from the surface of the Earth. To calculate the force of gravity on me from the Earth, I need to know how far away I am from the center of the Earth. And also how far away the center of the Earth is from the center of me. However, since I'm so tiny compared to the Earth, the center of mass of me, being somewhere in my belly, I'm sure, is not that important. The law of universal gravitation is given by the following equation. The force of gravity is equal to capital G. That's the universal gravitation constant. Capital G is equal to 6.67 times 10 to the minus 11 Newton meters squared over kilograms squared. That is a universal constant. That does not change depending on where you are on the Earth. That does not change depending on where you are on the moon or just floating in the depths of space. Capital G is always the same. Then you multiply that by the products of the two masses. The force of gravity depends on the masses of both objects. The gravitational pull of the Earth depends on my mass, but it also depends on the Earth's mass. The gravitational pull between the Sun and the Earth depends on the Sun's mass and the Earth's mass. And then finally, this distance r squared, where r is the distance between the centers of masses of the systems. So the difference between the center of mass, the distance from the center of mass of the Sun to the Earth, or the Earth to the Moon, or me to the Earth, and so on. So G, having these units, it means that you have to use the mass in kilograms in order to get the kilograms to cancel. You have to use the distance in meters in order to get the meters to cancel, leaving you with newtons as your force. So it is important to make sure everything is SI. You have kilograms, meters, seconds, all that fun stuff, before plugging things into this equation. Now, so this gives us the force of gravity, or the weight of an object, depending on this gravitational constant, the mass of a person, the mass of the Earth, and the distance from the center of the Earth squared, if you wanted to talk about the force of gravity or weight of a person. But we already had an equation for weight, right? Weight was equal to the mass of the object times g, the acceleration due to gravity, small g. Well, weight, or the force of gravity, was equal to the mass of the object times small g. Setting these forces equal to one another, we see that mass of the first object times small g is equal to big G times the mass of the first object times the mass of the second object over r squared. The masses here, m1, cancels. So G is equal to small g, the gravitational acceleration, is equal to the universal gravitation constant, big G, times the mass of the object, in this case the mass of the Earth, over the distance from the Earth squared. So if I know what the mass of the Earth is, and you can look that up, if I know what the radius of the Earth is, again, something you can look up, plug in these numbers, you find out G is about 9.80 meters per second squared. That's how we come up with that value. This is a more useful equation, or this rather, because it can be applied to other situations. What is the gravitational pull for a person in the space station? Well, it's not just the radius of the Earth then, but the people in the space station are above the Earth. You have to add that distance onto the radius from the center of the Earth. What is the gravitational acceleration on Mars? Well, if I know the mass of Mars and I know the radius of Mars, I can tell you how fast things will accelerate when you drop them on the surface of Mars, or on the moon, or on an asteroid. So this equation gives us g. Now, of course, the mass of the Earth here doesn't change with different people. You're standing on the same Earth that I'm standing on. The radius of the Earth doesn't really change. It does a little bit because it's an oblate spheroid, but we can pretend it is a perfect sphere for our purposes. So that's why everyone uses the same g, 9.80 meters per second squared, on the surface of the Earth when calculating the weight, because g is constant over, or approximately constant over, the surface of the Earth. Space station, g is a different value. When you move to a different planet, the mass of the planet changes. So you can actually calculate what your weight would be on different planets, moons, asteroids, and so on.